Before we touch a single setting, I want to set expectations and define the scope of what we're doing together.
The reference system is ASUS TUF Gaming Z790 Plus Wi-Fi, Intel Core i9-14900K, Corsair IQ Link Titan RX RGB 420mm liquid cooler, and 6 140mm fans in push-pull front intake. The chassis is a fractal design Define 7 XL. Memory is 64 GB, using two 32GB DDR5-6400 CL32 modules. Verify the kit label and XMP profile. Graphics are provided by an XFX Radeon RX 7900 XT.
We'll treat this build as a reference platform, but no two chips or kits behave exactly the same, and nothing here is a guarantee for your individual silicon. Overclocking always carries risk, up to and including degraded performance and data corruption if done carelessly. We'll proceed deliberately, verify stability at each step, and keep a clear path to revert any change. Let's begin with the official reference points. Intel lists the Core i9-14900K Ace as a 24-core, 32-thread processor with up to 6.0 GHz maximum turbo frequency, 125 watts processor base power, 253 watts maximum turbo power, official DDR5 support up to 5600 megatransfers per second, and a 100°C T-junction. Those are specifications and absolute limits, not daily overclock targets. In this guide, we will treat 90 to 95 degrees Celsius under sustained loads as a practical warning band for daily use. If temperatures, power, or voltage rise excessively, the recommendation is to back down. A cooler, more efficient system that runs every workload you care about without error is the real goal. One more crucial baseline. DDR5-6400 is, by definition, a memory overclock on this CPU platform. Intel's official DDR5 support for the 14900K tops out at 5600, and pushing 2x32 GB at 6400 can be more demanding on the CPU's integrated memory controller than running 2x16. We will separate memory tuning from CPU tuning so that you can isolate variables, find the integrated memory controller's limits, and choose a stable daily profile. You will also see an important correction in this build's parts list. The memory kit is described as model CMH64GX5M2Y6400C32C32, labeled Dominator Titanium in the supplied notes. Corsair model prefixes suggest CMH variants are generally associated with Vengeance RGB, while Dominator Titanium kits commonly use a CMP prefix. Do not assume the product family name is correct. Verify the physical label on your modules or the kit packaging, and use the XMP data actually stored on your DIMMs. We will not state an unverified product family as fact, and will use the profile information read from the modules themselves as the baseline. Finally, we will explain Intel's current guidance around instability on certain 13th and 14th generation desktop processors, including the vmin shift findings, why current motherboard microcode matters, and how to operate from Intel default settings as a stable starting point. A UEFI update can deliver the latest microcode and safer defaults, but a BIOS update is not a repair for already degraded silicon. With that in mind, let's prepare the platform and our thermal headroom.
Start with the cooling system, because thermal headroom is your performance budget. Our case is the Corsair 7000D Airflow, a large tower designed for high airflow. The CPU is cooled by a Corsair IQ Link Titan RX RGB 420mm radiator mounted at the front, in push-pull with 6 RX 140 fans. That means we have 3 140mm fans drawing in fresh air, and 3 more assisting push or pull through the radiator, depending on your exact bracket layout. The intent is simple. Feed the radiator with the coolest possible intake air, exhaust warmed air efficiently, and leave enough intake elsewhere to supply the graphics card and the motherboard's VRM heatsinks. Front-mounting a 420 with the tubes entering the radiator at the bottom side is often preferred for AIO longevity because it helps keep air bubbles away from the pump. For daily operation, use a firm, even thermal paste application and consistent block mounting pressure. In the 7000D, you have headroom to add top and rear exhaust. With a dense front radiator, top exhaust is valuable to avoid heat soak. Consider at least one rear 140mm exhaust. Your exact number of fans is less important than clear, non-conflicting airflow paths and fan curves that react smoothly to CPU and liquid temperatures. Take a moment to consider the bottom fan positions near the graphics card.
If you vertically mount the XFX Radeon RX 7900 XT, a bottom fan configured as exhaust directly beneath the GPU may end up fighting the card for air, potentially raising GPU hotspot temperatures. The correct orientation is not universal. Test bottom intake versus bottom exhaust by measuring GPU core and hotspot temperatures in a repeatable workload, and keep whatever is measurably better. The 7000D provides the space. Your job is to verify with data. Because we're using a push-pull array on a large radiator, expect strong thermal performance at modest fan speeds. That helps our noise floor and gives extra thermal mass for short boost bursts. Nevertheless, when we get into sustained multi-minute loads, a 14900K can hit or exceed 250 watts if allowed. That's where we will act responsibly. Watch liquid temperature, watch CPU package temperature, and keep sustained CPU thermals in the 90 to 95 degrees Celsius band at most for this guide. Intel's official T-junction is 100C, but you gain nothing by hammering the silicon at the top edge all day. Lastly, balance your fan curves. You can set a general chassis curve in the UEFI tied to motherboard or CPU sensors, and you can also manage the AIO and Corsair fans in IQ Link if that suits your workflow. Avoid overly aggressive step changes. Gradual ramps prevent oscillations in temperature and noise. We'll validate the net effect later in HW info, which will show you CPU core temperatures, package power, VRM temperatures where available, and liquid temperatures reported by your cooler. Stable thermals make the rest of this guide predictable.
The safest overclock begins with a BIOS update because we want the latest Intel microcode and the appropriate defaults before we ever raise a ratio. Intel has publicly identified elevated voltage and temperature as contributors to vmin shift instability on affected 13th and 14th generation desktop processors. Intel cites 4 scenarios: motherboard power settings exceeding Intel guidance, an EHTV boost algorithm issue mitigated by microcode 0x125, high SVID voltage requests mitigated by 0x129, and elevated voltage requests during idle or light load mitigated by 0x12b. Subsequent releases, such as 0x12f, continue to refine behavior. The action item for end users is straightforward. Obtain the applicable microcode through a motherboard UEFI update and operate from Intel default settings as the baseline. On the ASUS TUF Gaming Z790 Plus Wi-Fi, go to the official ASUS support page for your exact board revision and check the live BIOS listing. As of mid-2026, ASUS notes releases carrying updated Intel microcode for stability and security, and earlier milestones introduced Intel default settings and made them the factory default. Do not hardcode any specific version from this video into your workflow. Always check the live support page and read the release notes. Download the current BIOS, place it on a FAT32 formatted USB drive, and use ASUS Easy Flash 3 from the tool menu in UEFI to perform the update. If ASUS provides a separate Intel Management Engine firmware package, apply that as directed in their notes. Once the update completes and the board reboots, immediately re-enter UEFI. Press F5 to load optimized defaults, then explicitly select Intel default settings if your BIOS presents a choice. Keep voltages and multipliers on auto for now. This ensures you start from Intel's guidance on power limits and voltages rather than a board vendor boosted profile. Remember, a BIOS update can improve stability margins by enforcing more conservative voltage behavior and by delivering microcode changes, but it cannot undo damage from prior aggressive settings or thermal abuse. If your CPU has already degraded, no firmware can reverse that. While you're in UEFI, check that your SATA and NVMe devices are visible, confirm your boot order, and take note of key menus we will visit: AI Tweaker, Digi Plus VRM, and advanced settings such as internal CPU power management. We will take a conservative, one variable at a time approach. Before that, let's establish a measured baseline in Windows so we have numbers to compare against as we tune. Now establish a measured baseline with everything at Intel default settings and memory at JEDEC defaults. The goal is to measure what your actual machine does today with safe, known good settings so that you can quantify any change. Boot into Windows, apply current chipset drivers, Intel Management Engine, network drivers, and your AMD Adrenalin suite for the Radeon. Reboot once more to settle any driver initialization. Install HW Info, Cinebench 2024, OCCT, Prime 95, Y-Cruncher, MemTest86 on a USB drive for pre-boot testing, Carhu RAM Test or HCI MemTest for in-Windows memory stress, 3D Mark, and a few real games that you actually play. Open HWinfo in sensor mode and expand the CPU, motherboard, and GPU sections. We are going to log the following: CPU P-core frequencies and effective clock to reveal clock stretching, E-core frequencies, per core and package temperatures, CPU package power, V-core as reported by the SVID telemetry, VRM temperatures if available, DRAM data rate, memory controller clock where exposed, and GPU core, hotspot, and memory temperatures. Run Cinebench 2024 multi-core for 3 consecutive passes and record the scores, CPU package power, and the peak and sustained temperatures. Then try OCCT CPU for 10 minutes at a moderate thread count to warm the loop and observe steady-state behavior. We're not stress testing to breaking point yet. We're establishing the thermal and power envelope with safe defaults. Make sure you record ambient room temperature and the fan profile you used, because those variables materially change results. For the GPU, run 3D Mark TimeSpy once to confirm a clean baseline and that the card is recognized properly in Adrenaline. If your memory kit is already at JDEC, you can later boot MemTest86 from USB for a quick sanity pass. Do not mix tuning variables yet. Leave XMP off for the immediate baseline. The point of all this is to have repeatable data before we change ratios, voltages, or XMP. With that reference in hand, we can talk about CPU tuning philosophy. CPU tuning starts with restraint and with the recognition that this platform is complex. The i9-14900K blends P-cores and E-cores, a ring/cache fabric, and multiple protective mechanisms. The safest daily approach is to set realistic goals for thermals and stability, then work incrementally. We will prioritize adaptive voltage, measured behavior, and limits that align with Intel's guidance, rather than fixed high voltages. Adaptive voltage means the processor and motherboard cooperate to deliver the voltage needed for a given frequency and load state. That is paired with VDROOP, the intentional drop in voltage under load to prevent spikes and protect the silicon. Load line calibration, or LLC, changes how much the voltage sags under load. In practice, you want a moderate LLC that respects VDROOP. Extremely flat LLC can look attractive in a screenshot, but it may cause transient overshoot and worsen long-term reliability. We will not prescribe a universal LLC level because board designs and samples differ. Instead, we'll show you where it is set and how to evaluate results in HWinfo. Next, let's speak about limits. PL1 and PL2, often labeled long-duration and short-duration package power limits, constrain sustained and short-term power draw. Current limits, like ICC max and IAVR current limits, define how much current the regulator will allow on the core rail. Starting from Intel default settings keeps these limits conservative enough to reduce stress while still allowing high performance. Current excursion protection, or CEP, is another safeguard that can clamp transients. Keep CEP enabled during daily tuning. It is there to prevent unhealthy spikes. Ratios matter too. You can tune P-cores and E-cores separately and manage the ring/cache ratio, which ties together parts of the CPU fabric. Think of the ring ratio as something you keep comfortably behind the P-core ratio, not as something to chase for a hero number. For heavy AVX workloads, consider an AVX negative offset so that AVX heavy code runs a few bins lower frequency than scalar code, reducing heat and errors. Again, there is no universal offset. It depends on your workloads and your cooling. Finally, the workflow. Change one variable at a time. If you want to test whether your sample can hold a slightly higher P-core ceiling under Cinebench loads, move the P-core ratio up one bin, leave voltages on adaptive, keep limits at Intel default, save and boot, and remeasure. If you want to stop clock stretching under a specific all-core workload, try a small negative curve or adaptive offset instead of forcing a fixed high voltage. If you are approaching 90 to 95 degrees Celsius in sustained loads, accept that as your practical ceiling. Backing down 100 to 200 MHz for daily reliability is often the smart play. Watch for WHEA errors in Windows, for application crashes, and for any sign of throttling.
and save your known good states as UEFI profiles so you can always revert within seconds.
Enter ASUS Advanced Mode with F7 on the ASUS TUF Z790 Plus Wi-Fi, and let's map the important places. In AI Tweaker, you'll find CPU ratios, memory profiles, and core voltage controls. In Digi Plus VRM, you'll find load line calibration and related power delivery options. Under Advanced, internal CPU power management houses PL1 and PL2, tau timing, current limits, and current excursion protection. Start gently. In AI Tweaker, leave CPU core ratio on auto or set by core usage if you want to put gentle ceilings on the highest P-core bins without forcing a single sync-all value. For example, you may choose to cap maximum turbo bins under specific thread counts while leaving single-core behavior mostly intact. Do not jump to a fixed multiplier and a fixed voltage for daily use. Keep adaptive so the CPU can request appropriate voltage across states. Move to CPU core/cache voltage and choose adaptive mode rather than manual. Leave SVID behavior on auto or conservative profile rather than an aggressive trained or optimized mode that might raise voltage. We are deliberately avoiding exact numbers because your sample and this board's voltage mapping will differ from others. The goal is to measure, not to assume. In Digi Plus VRM, you will find load line calibration. Middle-of-the-road settings typically preserve intended V-droop, while extreme levels can flatten it to near zero. Start at the default and observe behavior. Compare idle V-core, load V-core under Cinebench, and transient spikes captured by HW info. If load voltage is drooping excessively and causing instability at modest power, you can try one step tighter. If transients are spiking, step looser. Always confirm with real measurements. Under Advanced, internal CPU power management, verify PL1 and PL2 are on Intel default settings and that CEP is enabled. You will also see current limits, such as IAVR current limit and ICC max. Leave them at default while you find your chip's stable ratios within the thermal budget. If you later choose to relax a limit, do so in small increments and remeasure power and temperature. This is a good time to mention E-core and ring ratios. In AI Tweaker, you can keep E-core ratios close to default or lightly tuned. Ring/cache ratio should typically trail P-core by a comfortable margin rather than chasing P-core frequency. If you see instability that looks odd, crashes that aren't power or temperature related, try reducing the ring ratio a notch. Now memory. In AI Tweaker, you'll see XMP1 and XMP II. On ASUS boards, XMP1 often applies the kit's primary timings along with board-tuned subtimings, while XMP2 tends to apply the profile more strictly as written in the DIMM's SPD. Neither is inherently better. Try XMP1 first for convenience, and if training or stability is finicky, try XMP2. Remember, DDR5-6400 is a memory overclock relative to Intel's 5600 spec, and 2x32GB is a heavier load for the memory controller. If training fails, trying XMP2 or stepping down one bin to 6200 or 60000 can save you time while you refine voltages. If you do need to explore memory voltages, you'll find DRAM VDD and DRAM VDDQ, often paired, plus VDDQ TX per DIMM transmitter voltage, VPP, and on the CPU side, System Agent, VCCSA, and the memory controller rail, often labeled VDD2 CPU or IMC voltage. We will not name fixed safe numbers. The rule here is simple. Avoid unnecessary voltage, make changes in the smallest steps your BIOS provides, and conform with long-form memory testing before declaring victory. Always save a working profile in the UEFI before you experiment. Memory tuning is a separate project because stability criteria and failure modes are different from CPU core tuning. Start by verifying exactly what memory you own. The kit described in our notes is CMH64GX5M2Y6400C32, and the notes call it Dominator Titanium. Because Corsair commonly associates CMH with Vengeance RGB, and Dominator Titanium kits frequently use a CMP prefix, do not rely on the product family name in a part list. Check the physical label on the DIMMs or the retail box. Then, in the UEFI, read the SPD and XMP data from your own modules. Those are the values you should start with. Enable XMP1 and see if the board trains and boots.
If training loops or memory fails to initialize, try XMP II. If both struggle, step the memory frequency down 1 bin to 6200 and try again. Remember, 2 by 32 gigabytes at 6400 is an overclock for the integrated memory controller, and your CPU's IMC may prefer a slightly lower data rate for daily use. It is better to run 6000 to 6200 clean with tight timings than to throw voltage at 6400 and chase marginal gains. Once you're in Windows at your target data rate, verify with HWInfo that memory is actually running at the expected speed. DDR data rates are double the actual memory clock, so a 3200 MHz memory clock corresponds to DDR5-6400 effective. Then begin testing. Run memtest86 from USB for a pre-boot pass. In Windows, run Karhu RAM test or HCI memtest for several 1000% coverage, and run Y-Cruncher multi-threaded tests which are sensitive to memory errors. Watch for WHEA events, application crashes, or even silent data corruption, any of which indicate that your settings are not stable enough for daily use. If you want to refine beyond XMP, do so in a controlled sequence. Primary timings include CAS latency, TRCD, TRP, and TRAS. Secondary and tertiary timings include parameters like TRFC, TRRD, TFAW, and many more. Do not random walk these values. Change one small group at a time, retrain, and test. On the voltage side, DRAM VDD and VDDQ are the primary levers, with small, measured increments if stability requires it. System Agent, VCCSA, and the Memory Controller Rail, VDD2 CPU or IMC, also influence training and stability, but increasing these unnecessarily can worsen heat and reliability. There is no universal safe number. The safe value is the lowest one that passes long-form testing at your chosen frequency and timings. Expect training time to increase at higher data rates or tighter timings. That's normal. If you see repeated training loops, postcodes related to memory, or Windows that boots but produces WHEA memory errors under load, back off. The smartest approach is to decide on a daily target, often the kit's XMP, and run exhaustive tests there, only layering on tighter timings after you have weeks of clean operation.
Once Windows loads, we verify that the system is truly running what you think it's running. Open HWInfo in sensor mode and confirm CPU P-core and E-core frequencies at idle and under a quick load. Confirm the DRAM data rate and confirm that the temperatures are sensible at idle. If you enabled XMP, verify the timing readouts to ensure the profile applied. If your board offers resizable bar, enable it in UEFI beforehand and check in Windows that Smart Access Memory is active for the Radeon. Update AMD Adrenalin to the current release for your card, then set the global tuning page to default for now. We'll tune the GPU later. In Windows Power and Battery, choose a plan appropriate to your needs. Balanced is fine for most. High performance or ultimate performance can be useful for consistency during benchmarking. Disable background tasks that inject variability into benchmarks, including cloud syncs, scheduled scans, and overlays you don't need. Now run a light verification round. Launch Cinebench 2024 single-core and multi-core once, not for the final number, but to make sure nothing crashes. Keep HWInfo visible and watch for any obvious red flags. A core parked at 0 frequency, package power that spikes and immediately throttles, or effective clock much lower than reported clocks under load, a sign of clock stretching. If you've made memory changes, run a quick round of Karhu or HCI for a couple 100% to flush out immediate errors, then plan for overnight testing later. The idea is to build confidence that this new UEFI configuration boots, idles, and handles light to moderate loads cleanly before we stress it. If you see WHEA warnings in the event viewer, fix them now. Don't normalize errors. They are messages that something needs to change. Voltage too low, timings too tight, a ring ratio too aggressive, or thermals out of range. With the operating system validated, we can move on to graphics tuning. Now turn to the Radeon RX 7900 XT and open AMD Adrenalin. Adrenalin offers automatic and manual controls, plus per-game profiles and a built-in stress test. Start on the Performance tab, then the Tuning sub-tab. Click to enable tuning controls. For a quick first pass, the automatic undervolt tool on supported products can trim voltage without changing clocks. That can reduce temperatures and fan noise while maintaining performance. Apply the automatic undervolt, run the built-in stress test for a few minutes, and then run 3D Mark Time Spy and one of your real games to validate. If you prefer manual control, switch to custom. You'll see a minimum and maximum GPU frequency slider and a voltage slider that sets the ceiling for the voltage frequency curve. Lowering the maximum voltage slightly while leaving the maximum frequency near default is a common way to find a more efficient operating point. Nudge values in small increments and test each change. Don't prescribe or copy a number from someone else. Two RX 7900 XTs from the same brand can differ by tens of millivolts and hundreds of megahertz in what they tolerate. Next, look at the VRAM controls. You can set a maximum memory frequency, and on some driver versions, adjust timing presets. Approach VRAM tuning conservatively. Artifacting and driver timeouts are your warning signs. You also have a power limit slider. Raising it allows the card to draw more power to sustain higher clocks, while lowering it can enforce efficiency. Pair this with a custom fan curve. Many users like to disable 0 RPM, so the fans spin slowly even at idle, but 0 RPM is perfectly fine if your case airflow keeps idle temperatures in check. Monitor GPU hotspot, not just core temperature, and watch memory temperature where exposed. If hotspot runs far ahead of core, revisit case airflow and the bottom fan orientation we discussed earlier. Make use of per-game profiles. A fast-paced shooter may tolerate a more aggressive fan curve and frequency target, while a quiet single-player title might benefit from a deeper undervolt for silence. The key, again, is measurement. Keep HW info or Adrenaline's overlays up during your tests, and verify stability with a mix of the Adrenaline stress test, 3D Mark, and long gaming sessions. If instability appears, including driver resets, flickering, or crashes, reset to default in one click and rebuild your profile in smaller steps. The reset to default capability is your friend. A benchmark score is not a stability certificate. It is a data point, and we need many data points across time and across workloads. Begin with CPU stability. Cinebench 2024 Multicore is a quick thermal and power sniff test, but it's not exhaustive. Add OCCT CPU tests, small and large datasets, and Prime 95 with and without AVX to probe different paths. Consider an AVX offset in the UEFI if AVX loads drive temperatures or errors too high. For mixed integer and floating workloads, Y-Cruncher is excellent. Choose multi-threaded tests that run for 10 to 20 minutes per pass and watch for any error or non-deterministic output. For memory, combine tools. MemTest86 Preboot can catch glaring problems. In Windows, run Carhu RAM Test or HCI MemTest for thousands of % coverage. Memory errors can be sneaky. A single flipped bit can corrupt an archive or a project file without an immediate crash. Don't cut memory testing short. If you see any error counter increment, back off your frequency, relax a timing, or reduce stress on the memory controller before you consider adding voltage. The safest change is the smallest one that restores clean operation. For the GPU, loop 3D Mark Time Spy or Speedway, and then pivot to actual games. Some engines stress shader compilation, some saturate VRAM, and some hammer the raster or the compute pipeline. Keep an eye on GPU hotspot in HW info and in Adrenaline. If the hotspot routinely brushes the card's thermal limit and clocks swing up and down, you'll see inconsistent frame times. A modest undervolt, a slightly higher fan curve, or a revisit of bottom fan orientation can cure it. If clocks appear normal but performance sags, look at effective clock on the CPU. Clock stretching on the CPU can bottleneck your GPU. Log your sessions. HW info can log to a CSV. Mark down ambient temperature, the profile you ran, and any anomalies. WHEA WHEA errors, thermal throttling flags, power throttling, or VRM temperature spikes. Remember our sustained CPU thermal guidance. If you regularly hit 90 to 95 degrees Celsius or see package power surge above what your cooler can sustain, that's your cue to step back a bin or to tighten power limits. Avoid the trap of chasing a single higher number at the cost of broad stability.
When in doubt, more conservative settings that survive days of varied workloads are superior to an edge profile that squeaks through one test.
When a setting fails, remain calm and methodical. Many failures are recoverable in seconds if you follow safe procedures. If the system fails to post or enters a memory training loop, shut the system down fully. Then, switch off the power supply, unplug the PSU from the wall, and discharge residual power by pressing the case power button for several seconds. Consult your ASUS motherboard manual for the location of the clear CMOS pins or button. Use the documented procedure, often a shorting tool or a dedicated button, to clear settings. Wait the recommended interval, reconnect power, and boot. This resets the UEFI to defaults.
For a corrupt BIOS or failed update, use only the procedure documented for this exact board. The TUF Gaming Z790 Plus Wi-Fi manual specifies ASUS Crash-Free BIOS 3. Download the latest BIOS, rename it asus.cap or tgz790pw.cap, copy it to USB, and follow the manual. Do not shut down or reset during recovery.
Do not guess or use instructions written for a different ASUS model. For boot loops after an aggressive memory profile, step down one frequency bin or revert to JDEC, then re-enable XMP 1 or 2 after verifying a clean boot. If Windows boots but you see WHEA errors, start by relaxing the ring/cache ratio, then consider a slightly lower P-core bin. Then verify that CEP and Intel default power limits are still active. If stress tests crash instantly at load ramp, your LLC may be too flat. A little more VDRAM can improve transient behavior. Thermals are a common culprit. Recheck the cooler mount, paste spread, and fan orientation. Remember our airflow note. A bottom fan set as exhaust beneath a vertically mounted GPU can starve the GPU. Test bottom intake versus exhaust to see which delivers a cooler hotspot. If your VRM temperatures climb unusually high, consider adding a targeted side or top intake to sweep that area, or lower sustained CPU power by tightening PL1 and PL2. Always maintain a set of saved UEFI profiles, baseline Intel default settings, baseline plus XMP, and then each experimental step. That way, a failed attempt costs you seconds, not an afternoon. And if a BIOS update alters behavior, because new microcode can, go back to your baseline, validate, and then retune. Never assume a new BIOS behaves like the previous one.
Finally, compare like with a repeatable methodology. Construct a simple table for yourself with test scenarios and run each with the same ambient room temperature, the same Windows build, the same drivers, and the same background processes disabled. Suggested scenarios include 1. Intel default settings with memory at JDEC. 2. Intel default settings with XMP applied. 3. CPU tuned with adaptive voltage and your chosen limits, memory at JDEC. 4. CPU tuned plus XMP or your validated memory profile. And 5. CPU and memory tuned with your final AMD Adrenalin GPU profile. For each scenario, run 3 passes of each benchmark and record the average, with outliers noted. On the CPU side, use Cinebench 2024 single and multi-core, 7-zip or another compression suite, and a Blender project render if you use it. On the mixed workload side, run Y-Cruncher. On the GPU side, 3D Mark TimeSpy or Speedway is a good anchor. For real games, choose a fixed route and settings in a few titles, such as Cyberpunk 2077, Starfield, Microsoft Flight Simulator, or whatever you actually play, and record average FPS and 1% lows. Also record CPU package power, peak CPU temperature, and GPU hotspot during each run. The video should insert measured values captured from the actual machine, with no fabricated results, and should note the ambient temperature and driver versions in an on-screen caption. As you compile results, look for the pattern. XMP often adds a noticeable bump to minimums in CPU-limited games and to some content workloads. A carefully tuned CPU profile can sustain higher clocks within the same or lower power envelope compared to a board-boosted default. A modest GPU undervolt frequently stabilizes clocks by reducing thermal throttling, improving 1% lows and acoustic comfort. If any scenario produces WHEA profiles, clock stretching, or throttling flags, it doesn't graduate to daily. Back it down. To close, let's recap the core principles.
Start with the latest UEFI and Intel microcode and load Intel default settings. Respect the platform's complexity. Adaptive voltage, VDRAM, LLC, CEP, ring ratios, E-core ratios, and AVX offsets all play a role. Treat DDR5-6400 as the overclock that it is, especially on 2x32GB kits. Train and test thoroughly, and use only as much voltage as you need. Keep sustained CPU thermals in the 90 to 95 degrees Celsius band for this guide, recognizing Intel's 100 CT junction as a limit, not a daily target. Verify stability with multiple tools, including Cinebench 2024, OCCT, Prime 95, Y-Cruncher, Memtest 86, Kohu or HCI, 3D Mark, and your actual games. Monitor for WHEA profiles, clock stretching, thermal throttling, GPU hotspot behavior. If a change pushes temperatures, power, or voltage too high, back down. Save UEFI profiles so you can always revert. And remember the small but important details. Airflow orientation tests under a vertical GPU, bottom intake versus exhaust verified by measurement, and careful one variable at a time tuning. Thank you for spending time on this deep dive. The narration you're hearing is recorded with a clean, consistent, non-whispering professional tone, with careful pronunciation of acronyms, including UEFI, XMP, PL1, PL2, VRM, WHEA profiles, and HW info, and we've ensured transparent editing without clipping or distracting artifacts. If this guide helped, consider subscribing for more measured, data-driven optimization. Your results will be your own. Make them stable, make them efficient, and enjoy the machine you built.